Good evening, everyone. Welcome to tonight's talk, the Cornubian Batholith, an introduction to the geology of Dartmoor. Whilst people are still arriving and getting settled down, I'll make a start. My name is Andy Bailey, the Outreach and Interpretation Officer for Dartmoor National Park, and it's my pleasure to welcome you all here this evening. And it's great to see so many of you who've tuned in for tonight's presentation and talk. So welcome all of you. As you can see, we've made the move over to YouTube, and I hope that this will improve your experience with us tonight. It should certainly avoid any feedback issues and the rustling crisp packets that we might have heard in the past. Right, so tonight I am very pleased to be joined by Andrew Griffiths, who works with us here at Dartmoor National Park as a volunteer Dartmoor education guide. Andrew has had a full and long career as a geologist, teacher and geographer, working for international companies and inspiring students of all ages with the subject. When he's not leading school parties around the moor for us, he continues to lecture on volcanoes and earthquakes to the U3A and to other volunteers. And he also works as an educational consultant. Tonight, Andrew is going to talk about the Cornubian Batholith, a phrase that always makes me feel like I've developed a bit of a lisp. And he's going to give us an introduction to the geology of Dartmoor. So, ladies and gentlemen, I'm going to hand you over to Andrew Griffiths, if I could get the screen sorted. Andrew.
Thank you very much. Can you hear me? Yeah. Welcome, everybody, and thank you very much for the kind words at the beginning. This is a first for me in terms of a virtual lecture or talk, and so I hope you'll bear with me because it's quite interesting looking at a screen and not actually seeing any faces. But I assume that you're all watching and listening because you have a sort of love of Dartmoor, that wonderful wasteland close by to us all. And I work on the principle that the more you know about a place, the more you can understand it, and the more you can understand it, the more you can love it. And so hopefully after today's talk, you will have a little bit more knowledge about things you didn't know about. And as Andy says, we hopefully will have time afterwards to have some questions so we can sort of investigate some of the topics further. I'm immediately saying that I've bitten off more than I can chew here. I'm not an expert on Dartmoor. I'm doing a part-time PhD on the volcanoes of New Zealand and their risks to tsunamis there. You might read in the news in the last 4 or 5 hours, there's been quite a large earthquake in northern New Zealand, and there is a tsunami risk. I've just literally checked now, and they've turned that off. So I am coming from this in a very similar way to you. In the first instance, the maps of Devon, the geology maps of Devon, were produced like this by two gentlemen, Reverend Sedgwick and Murchison. And interestingly, the rock type identification that they have put forward in the late 1880s has changed very little indeed. And if you look at the modern day geology books and articles, they are still talking about the same rock types. A type rock type, the Devonian, in this, it's the only county in the UK which has got an era, geological era named after it, for good reason. The reason why I'm interested in it is, you know, a shale is a shale to me, and I'd like to put it in context. And the context which they didn't have when they were producing these maps was, of course, plate tectonics. And how does the idea of dodgem carved continents bumping into each other and moving away relate to our understanding of the geology of Dartmoor, and in particular the granite of Dartmoor and surrounding metamorphic rocks. So for those who know all about plate tectonics, I apologize, but I'm going to do a very brief summary of the plate tectonics as it relates to Devon and Dartmoor, so that we can again put it in context. At the end of the day, you can come away with no idea of where the various rock types are. But if you get a feeling for why the bumping of plates together has allowed the economic mineral exploitation and the landscape that we see and love, then we'll have got somewhere. So that map hasn't changed very much since Murchison and Sedgwick produced it, but our ideas of the geology have changed a lot. And so what I will do is briefly talk about plates, then look at the Devonian rocks and the Carboniferous rocks, which were laid down before the collision took place, and roughly between 400 and 285 million years ago. We can be more specific nowadays because of radiometric dating. And then we had the Veriskan orogeny, which is a big collision zone, equivalent to the Himalayas or the Alps. Then we'll look at how the granite batholiths were emplaced in both Devon and Cornwall, and then how they were altered, and then concentrating the minerals that we exploited. And then we look at some of the surface features due to various types of weathering and erosion, and look at obviously some of the minerals that have been exploited in the area. So that's the plan. And this, you've probably all seen this. It's a rather nice one, of course, because it does things in 3D, but this is a cross section of the Earth, and you can see that the lithosphere is basically, let's be general about this, the crust, the mantle is below that. And just for those people who were reading the news, if this was New Zealand, there is a subduction zone, and the earthquake that happened today, 7.3, happened about 90 kilometers down there. So you can see why they're a bit worried about tsunamis and things. So we've got then 3 different types of plate boundary, where the plates are coming together, where the plates are moving apart, and where the plates are running side past each other, which is this one here. And these side strike slip faults, which I've got my arrow on, I hope you can all see the arrow, are quite important when it comes to the structures of the orogeny, the mountain building activity that hit the southwest of England. So we'll come back to that. A nice clear black and white cross section. There we go. That's it. So here we would have, for example, the mid-Atlantic ridge opening up and splitting Europe from America as an example. Here we've got and Iceland as another one. Here we've got, say, New Zealand and all the Pacific islands, including Japan, Indonesia, and Philippines. And then here we've got the major subduction zone that runs all the way down the South American western coastline and causes, and obviously there south of Japan, and causes the big mega earthquakes, the +9s that we experienced obviously in 2014 and again in 2015. So, sorry, 2004 and 2011, I'm not talking about. So hopefully you're all happy with this idea. And if you're not, just think dodgem cars. And there are times in the dodgem cars when you're going around and you're bumping into each other. There are times when you're moving apart. And then there are times, of course, when you all get stuck and you're sliding past each other. And if you think of plate tectonics like that, you won't go far wrong. And so before the times when we are really interested in, the plates were moving around, as we can see from these 2 diagrams. So pre-Devonian, so about 450 million years ago, this was what the Earth would have looked like. And you can see that through time, up until the Devonian, the continents, 2 large continents, were moving towards each other. And we're interested in this because, firstly, we are just here in this little microcontinent called Avalonia. Some of you might well have heard of the Iapetus Ocean, which runs across here, and less of you probably will have heard of the Rheic Ocean, which runs to the south. And what happened was these 2 great big plates, Laurentia and Gondwana, moved towards each other and eventually collided. And it formed, well, again, some of you will have heard of, the major supercontinent called Pangaea. Now, it's relatively unusual that all the land masses form one great supercontinent, and the Pangaea was the last time it happened. And so you can imagine the impact it might well have on things like climate, ocean currents, as well as things like evolution, because the various animals that lived at that time could freely move across the land masses and things. So plates moving together, plates coming very close to each other. The Iapetus Ocean disappears completely, and the Baltic bumps into Laurasia, and eventually becomes Laurussia, because it joins obviously parts of Russia. And here is Britain, but you'll notice that the Britain there doesn't have us on it. And in fact, we are part of that part of the Avalonia, and will join with Brittany and other parts of France and Spain, Iberia, when Armorica comes in and the Rheic Ocean closes. And if you just look then at these, as they start coming together, the Iapetus Ocean closes. We're in that yellow zone there, the Armorica one, and then eventually the Rheic Ocean closes, and then we get one great big dollop of land, which we call Pangaea, and we are just in there, in that shaded zone there. And that's when it all really then starts. And the reason why it's all very important is because we are part of this very small continent, the microcontinent, and bits of it are still, because of the collision, pushed down underneath the southwest of England. And they've done some fairly deep seismic studies there to find bits of those crustal fragments. It started as an island arc, just like Japan or Fiji or any of the Southwest Pacific islands. Then it broke away from Gondwana. And then when Laurentia and Gondwana collided, as we've just seen, Avalon was stuck in the middle. As you can see here, Avalon stuck in the middle and jammed closed. That became the center of the Pangaea supercontinent. And then eventually, just for the future reference, Pangaea broke up. And as it went apart, it basically started forming the Atlantic Ocean. And there's bits of Avalonia on the east coast of America, around Canada, and there are bits of Avalonia on this side as well. So it's been split open on both sides. And there's a little schematic. We are at number 5 there. And as you can see, as Iapetus Ocean closed up, then the Rheic Ocean opened up, and then Gondwana met Laurentia, and that closed up, and we had the collision. And the whole point about those collisions is that when you pull two big continents together, they don't do it gently and they don't do it fast. And so what you have is major compression, and the crust, even down to into the mantle, gets deformed. And so you get lots of basins and lots of ups. So you get highs and lows. And as you can imagine, if you try and bend rock, even at pressure where it becomes much more mobile, breaks occur. So it's not just folds, but it's great big faults that crack open. And the basins are very large basins that will change with time. And so the basins become troughs, then they become highs, then they go back to being shelves. And so they go up and down a bit like a yo-yo. And the reason why that's important is because when they're in the deep water, you're going to get certain types of sediment. You're going to get fine-grained sediment that carries out into the deep water. When they're in shallow water, you're going to get tropical limestones, for example, and coral reefs and sands and delta sediments. And of course, when they're out of the water, you're going to get surface deposits like what we call aeolian sand deposits or coal deposits from the swamps. So the tectonic history of this area is fundamental to understanding why the Devonian and the Carboniferous rocks in the southwest are as they are. So here we've got a series of basins. We'll look specifically at the Culm Basin because, as you can see, DG stands for the Dartmoor granite, And on the north of it, we've got the Carboniferous, and to the south, we've got the Devonian. And so we'll be able to see the variations in how the granite being pushed up into these rocks affects either of them. And now this is just a more modern version of the Sedgwick and Murchison rock. And from that, you can see that the Carboniferous is the white, and the blue and browns here are the Devonian. And you can see there's quite a distinct line running through here. What you haven't got, and I think there might be, if we have got on another map, I'll refer to it, but there's a dirty great big fault that runs through here called the Stickle Path Fault. And that is a strike slip fault that runs from sideways. So there's very little vertical displacement, but there's lots of horizontal displacement. The equivalent today would either be the North Anatolian Fault in Turkey, which is regularly moving sideways and causing quite a lot of disruption, or probably more famous, the San Andreas Fault, obviously in California. So these are the rocks that we're interested in. And as you can see, the red dollops, the granite masses, run all the way from Dartmoor to the east to the Isles of Scilly, which are down here. Now, when it came to these basins being filled up in the Devonian times, about 400 million years ago, the Devon was south of the equator in a relatively tropical climatic zone. And it was relatively shallow water. So we had shallow sea deposition for most of the, especially the early Devonian, and continental sand dunes and things like that. You wouldn't be surprised to learn that with all this bumping going on, that there was some volcanic activity as well. So we got volcanoes with some basalt coming in, which is a dark, runny sort of lava, and dolerite, which is approximately the same composition, but coarser grained. Once the mountain building took place, you can imagine mountains the size of the Himalayas or the Alps or the Cairngorms as in the past, and the Appalachians. You can imagine these high mountains being very easily eroded. Think about the weather conditions, you know, the cold and the amount of water running off them. And because of that, lots of erosion took place, and the sands and the muds ran down the mountains and into the basins, the sea basins, and filled them with thick deposits: muds, sands, sandstones, slates, and limestones. The volcanic activity came along as well, and more importantly, for historic reasons than the basalt and dolerite, is the volcanic ash. You've seen it from the Iceland eruptions and Mount Pinatubo and Mount St. Helens. The ash, when a volcano explodes, covers a very large area, and therefore it's much more useful in sort of working out what was where in the detective story of the geology of the southwest of England. So the basins filled up, and through time the waters got deeper, and so the coral limestones of the shallow water gave way to cherts. Now, cherts is a silica-based rock, very hard, and basically it forms as silica because it goes below what's called the carbonaceous compensation depth. Calcium carbonate cannot form, and so silica forms instead. So you've got an idea that it's got to be deep water. And so in sum, the the Devonian rocks of North Devon are overlain by Carboniferous, as we'll see in a minute, but in the South Devon area, those rocks are left exposed. One other thing that happens to all these rocks, though, is, as you can probably guess, as they get further down in this sequence and get deeper and deeper underlying all the other rocks above them, the temperatures and pressures go up, and slowly over millions of years they get baked. And it's the equivalent, and I'll use the analogy later when we talk about the other types of metamorphism, it's the equivalent of baking a steak. In this country, throw it on a frying pan, give it 2 minutes on each side, and then chuck it out. Whereas if you go to the States, southern states, they wrap it in tin foil and they put it in the ground for a day, and they bake it slowly. you get the same result at the end, or some would argue the slower cooking is better. But basically, you can get rocks baked very slowly, even if the temperatures are not particularly high, because we're talking such a long time scale. So to the north of the granite batholith, we have the Carboniferous rocks, which came later in the sequence of basins going up and down as the mountain building took place. Again, the rocks are very varied. They're sands and gravels and things like that. But the sea levels went up and down. And the reason why that's interesting is if you go across the coastline to Wales, you will find obviously that the Carboniferous is famous for its coal. And it comes as a sequence with millstone grit, which is a sand, and limestone, which is a shallow water deposit, because it was sort of the swamplands of Florida in South Wales. Difficult to believe if you've ever been to South Wales, but it's got the water there, but that's about it. But basically, these are called cyclothems, i.e., the sea levels go up and down in cycles. And each time it changes its sea level, different rock types are there. In North Devon, it was too far away from the swamplands, and it was in the proper marine section, and so we get the leftovers. We get the sands and the clays, and volcanic ash layered there as well. And this collision zone really started taking effect in the end, towards the end of the Carboniferous, and so that's when folding and faulting and graben structures, these block structures, started forming and allowing great thicknesses of the rocks to form, particularly in North Devon. And if you go to North Devon, Bude, for example, you will see some fantastic folding of these Carboniferous rocks, sort of chevron-style folding. And if you went underground, you'd actually find some fantastic faulting as well. I don't know whether this makes sense or not, but I just did it as a sort of cartoon, so that you just got a feeling for what it was. Here's South Wales. I've deliberately not tried to copy the coastline, because of course in those days it was nothing like this. These shallow seas and swamps ran down eroded material into the shallow waters. They piled up on the slopes, and occasionally an earthquake would shake these rocks, these sediments, which were very loose, and form what's called turbidite currents, which are underwater landslides. They settle on the seabed as very fine-grained rocks, which compact to form quite hard rock, and the deltas and fans do exactly the same. And so as we moved south towards North Devon, we go into deeper and deeper water, finer sediments and chert, and if we kept walking, we'd hit the front, the mountain building front from the south, which is causing all these problems. So in a nutshell, a complex sequence of different types of rock types. It doesn't really matter which ones at this stage, as long as you appreciate that, you know, the mountain building has had a major impact on what those rock types are. And then we get to the more, well, not the more interesting bit, but the next stage, if you like, when this batholith series intruded into both Devon and Cornwall over a 25 million period. And it's worth just noting the timescales we're talking here. The mountain building period of the Beriscan, which we'll look at in a second, lasted over 100 million years. The intrusion of the batholith, or series of batholiths, lasted 25 million years. These are very long periods of time. And so this is then the Beriscan orogeny. And as you will see, here is where we are on this dotted line, and it's part of the Avalonian thing. And we're going to just look a little bit about these different rock types in a second, because these will then determine where our minerals and where our granite is going to form. So there we are. There's Spain as it is now, Brittany, and then we come into the Rhine and Hessian region, and of course this zone here is the current Alps. So in many ways they're interlinked, but you'll notice that, and it's approximate here, but most of the lines of folding and faulting are running a very approximately west-east. And so most of our structures run approximately west to east, and that you will see throughout this whole area. And this again is a more detailed thing, but what it shows is that the different rock types in this mountain building have a very complicated history, in the sense that when they compressed and collided with each other, they just didn't bump into each other with a chocolate jam. So think of the Dodgem cars as bouncing on top of each other. And so one car lands on top of the other car. Hopefully the driver gets out beforehand. Now, these big bumps and folds are called naps, and they are very important in the southwest of England. They are very important up in Scotland, because wherever there's a mountain building period like the Biscay, or up in Scotland, the Caledonian, which incidentally was happening approximately the same time as this, you're going to get a very complicated sequence of rocks where normally you'd expect the oldest rocks to be at the bottom and the youngest rocks to be at the top. But if you've got a Dodgem car bumping going on and the old car lands on top of the younger car, you can get an inversion of age where the old are on top of the young. And these nap structures make life very complicated because they don't do it nice and cleanly. The terrains, or these big slabs of rock that move on top of the others, I come from somewhere else, are called allochthonous. And you can see on the bottom left here, the brown is allochthonous, and you can see that this part of the world is allochthonous, whereas the green regions are allochthonous. We'll come to some ones that haven't moved. There aren't many around, but they're called autochthonous. So we'll see those in a minute. But just think then of a major crash and cars on top of each other. I don't want to be too morbid about it, so we'll take the analogy no further. But it means that some of the old rocks are on top of some of the younger rocks, and there's lots of folding and faulting in between, which means when you're trying to understand the geology of the region, it is very difficult. And people like Murchison and Sedgwick didn't really realize that these rocks were of that sort of ilk, and believed that the basins just went up and down through God's gift. And so we've got these different rock types. So you'll see that the Devonian, the browns here, are allochthonous. And the purples, which are the carboniferous, are autochthonous. So these have not been moved. These have been dumped, okay, on top of the younger rocks. So they're inverted. The browns are inverted. And this was the situation before these granite batholiths were in place. So complex. It gets even more complex down on the Lizard, where, of course, some of the great lavas and rocks, pentanites and things form the Lizard complex, which was just previous to all this emplacement. And so what we've got then is extension and compression as the two plates, Gondwana and Laurasia, sort of come bumping into each other. And once they bumped into each other, there were places when they moved apart. There were places when they were moving together with the triangles, and there were places where they were sliding past each other. So in this region here, we've got a example of the three main types of plate boundary. And so it does make things obviously a little bit more complicated. And the other thing that's quite interesting, this rift here, the Bay of Biscay Rift that came up, it tried to, when the Atlantic Ocean was opening up, it tried to come through here and up the North Sea. And just as an aside, if that rift had taken place and it got jammed, the reason why it didn't, it got jammed because of the other complexities going on. But if that rift had carried on, then the Atlantic Ocean would be lying between us and Norway and us and France. And we wouldn't be talking Brexit at all, because frankly, we'd be part of Newfoundland. And you can think about the historical implications for the world if we hadn't been fighting all the wars in Europe, etc., etc. So we are either lucky or unlucky, depending on how you look at it, that the jamming of the rift here up the British-English Channel, rather, the southwest approaches, took place, and we stayed lodged into the Eurasian part, the Eurasian plate. So in summary then, the Variscan orogeny was about 400 million years in the making, happened at that same time as the Caledonian orogeny, which is happening in the north. So Britain that time was undergoing two major mountain building activities. Great for the geologist. I'm not sure you'd want to live at that time. The Rheic Ocean, which was separating Avalonia with Armorica, sort of got lost and disappeared. And major fluvial and marine rocks happened in the Devonian, carried on in Carboniferous times. But the types of rock that happened very much depended on whether there was compression going on, or extension, or side slipping, or faults foaming, things going up as blocks or going down as troughs. It all very much depended on when and where the mountain building activity was taking place. And in summary then, and I've got these, by the way, obviously I'm moving through them quite quickly, but I've got these on a PowerPoint, which I'd be happy for anybody to have. So if we go from the bottom, then Lower Devonian, we've got fluid shales and limestones. And as you work your way up, you think this all looks very much the same. And to some degree it is. And the only thing that's changing, if you like, is the sea level and the types of rock being eroded. That's until we come to where volcanoes start taking a fairly major role. And that, of course, is in the Upper Carboniferous here, and into the Permian here. And that's when we're moving on to now. So in sum then, I just put this in because it's by Shirley and Wilkinson, the references in the bibliography. It just puts together all the activities that are taking place as a sort of Venn diagram. Right, just a glass of water. Where you've got basements going up and down. You've got magmatism, both surface magmatism and underground magnetism in terms of the granites. And you've got mineralization taking place and sedimentary basins. So it just summarizes then what's happened for that period between the Carboniferous to the Permian, when in fact we get granite being emplaced. And so we'll move very quickly through this, but in principle, we've got granites. They're called S-type granites because they are predominantly biotite muscovite granites. So the two types of mica granite, which have two types of feldspar in them, the alkali feldspar and the plagioclase feldspar, bearing in mind that the majority of granites, well over 60%, is quartz. But since most rocks are made of predominantly quartz, it's not much point trying to identify rocks by the quartz. Two very important aspects to the granite rather than just the granite itself. Firstly, it's very coarse-grained, but there are areas where it's quite fine-grained, and there are some areas where it's very, very coarse-grained. Now, when it's very, very coarse-grained, we call it pegmatites, and when it's very fine-grained, we call it aplites. They are important on the economic aspects, so we'll come back to those later. But the main granite itself is basically a mica, feldspar, quartz rock, coarse-grained with large crystals of feldspar. We call the large crystals phenocrysts, and they are very indicative of slow cooling. which is what you'd expect because it cooled underground. And deep seismic studies have shown that the batholiths, and I'll just go into here now so you can see them. These batholiths are linked, and so I've got the ages there for them, and you can see that the coarse-grained batholiths are the sort of burgundy-coloured ones, includes Dartmoor, some of St Austell, and down by Land's End, and the fine-grained batholiths include Bodmin and Camanellis and parts of the Isles of Scilly. And you'll notice that the older emplacements, the blue ones, are the fine-grained ones, and the coarser-grained are the younger ones. So they didn't all happen at the same time. They happened over about a 22 million period, 25 million year period. So they did happen at different times. And fine-grained suggests that they cooled more quickly than the coarse-grained. And so it's a bit of a conundrum. But anyway, the rocks placed from the side scan evidence show that the rocks were placed as sheets. So if you can imagine a sheet of magma underneath here, and little plumes rising up and punctuating through the surrounding rock. So these are sheeted in the original formation. And if we look at the way in which they've formed, as it were, you'll notice on the right-hand side, then, this is a magma batholith coming up through the rock. Either in the north, it would be the Carboniferous rocks, and in the south, it would be the Devonian rocks. And basically, it bakes the sides, and it bakes the surrounding sedimentary rock in a zone called the metamorphic aureole. And it has chilled margins on the granite itself, and the rocks it intrudes into are baked and changed. And it's this changing that means that they can become economically interesting. And the whole point about it is that there are various ways in which minerals such as copper, tin, tungsten, increasingly more interesting things like lithium, beryllium, are all sent into a mobile mode and are reconcentrated in different parts of the region. Sometimes those regions are in the granite as veins, and sometimes they are in the actual host rock themselves. It doesn't need much concentration of some of these elements, copper and tin, obviously things like silver and gold and arsenic, to make them economically viable. So they're in the rock, they're in the granite, or they may be diffusely in the host rock, but they're not economically viable. And yet the baking granite coming up into the host can actually cause them to concentrate. And it can do it in a few ways. The two big ways, important ways, are firstly, the magma, as it cools, allows some minerals to crystallize, and some minerals won't crystallize until a later time. And those heavier crystals will sink to the bottom of the melt, the mix. And so your iron-rich, for example, minerals, being heavier than your aluminium-rich minerals, will actually concentrate at the bottom of the pile. And it's not always at the very bottom of the batholith. So you can get concentration of economically viable minerals by settling out. You can get it by the fact that when rock cools, particularly granite, and when it cools slowly, cracks appear. Just like when clay dries, if you're going around in the summertime on cricket pitches and there's no grass there, you'll see that the cracks appear in the clay. as contraction takes place. Exactly the same happens in the granite. These cracks appear as both vertical and horizontal joints, and the volatiles, the water and the gases from the material, the magma coming up to the surface, escape through these quick exits through the joints and out to the surface via the host rock. These are hot brines. They're not just water, they've got lots of chemicals in them and are very reactive, and therefore can dissolve minerals both as they travel through the granite and as they travel through the host rock. And when they start cooling down, they release those, they come out of solution, these elements, in a concentrated form, because different elements come out of solution at different temperatures and pressures. And so we do have within veins and dikes minerals at a concentrated level. Admittedly, there's still a lot of other stuff there as well, mainly quartz, but they are much more concentrated in these veins than they were beforehand. And those are the things that the miners are looking for when they're out to get the minerals for extraction. What the minerals are, whether it's gold and silver, whether it's tin or zinc, or whether it's iron, or whether it's copper, very much depends on the actual composition of the granite and the rocks in which the granite intrudes. And so, although there was lots of, for example, copper in Cornwall, and you get gold in there, and lots of arsenic and things, very much sulfide based, in Devon, the mines are much more tin based. That's not to say there isn't copper, much more tin based because of the rocks into which the granite intruded. Yeah, I'm going to show you close-ups, so they didn't come out too well, so I've just got some bigger pictures in a second. But as you can see, there's the granite, there's the muds and the sands and things that have been unaltered, and this is the baking zone. Very close to the granite, the rock is really baked hard, and so it becomes a very hard rock, which we call hornfels. And obviously the granite itself on its margin changes as well, because it's in contact with the hornfels. As you move away, you get spotted rock, and the reason why it's called spotted rock, it's got little dots of different rock drops have different things. Sometimes it's garnet, sometimes it's andalusite, as in the case in on Dartmoor, but it's just different temperature, a lower temperature and a lower pressure. You'll note, of course, that most of the contact metamorphism forming these aureoles around the granite are at relatively low pressure because, of course, they're near the surface. So they're hot because we're talking 1100 degrees centigrade, but low pressure. Whereas in the middle of mountain building activity, the pressures are much, much higher, and the temperatures are relatively high as well, but not as high as 1100 degrees. So you're going to get different types of metamorphism there, and therefore different types of minerals. So that's what we're all talking about then. That's granite. The translucent stuff doesn't look very much, but it's about 60% of the rock, and that's the quartz. The black is bits of mica and also tourmaline, which the feldspar, which is the yellow stuff here, and some of the white stuff, the feldspar crystals, there's one feldspar crystal, will weather to form tourmaline. So there's another big feldspar crystal, and as you can see, I haven't got a scale in here, but basically they can be centimeters in size. You need to only go to Haytor or Houndtor, and you'll find very large crystals. And actually, you can walk around the streets of Exeter. If you stand outside the Royal Albert Museum, there are crystals the size of your hand on the pavement. People just walk over it and stub their cigarettes out and chewing gum and everything, and I think it's an absolute disgrace, but anyway, that's another matter. This is the Hornsfels, and you can see by its conchoidal fracture that actually it's a very hard rock, and it's very important in relation to one of the economic mining activities that goes on here for aggregate. If we go back to the granite, the mining of granite like that is for building purposes, because you can imagine your kitchen work surface that polished up, nothing's going to burn it, and it looks very pretty, and it's a nice talking point if it comes from Dartmoor and you live nearby. So these are the major ways in which the granite and its surrounding rocks can be mineralized. And I won't spend too long just because I've gone through most of it. The only thing I would focus on is that hydrothermal activity, where hot brines dissolve and concentrate minerals, is one of the most important aspects of mineralization in the Cornubian batholiths per se, and Dartmoor obviously in particular. One of the odd ways in which that happens is something called metasomatism, where under certain temperature and pressure conditions, fluids and gases, either volatiles, the moving parts of the magma, will come out, and increasingly we realize just how much volatiles there are in magma. You don't realize it when you see this lava pouring over the surface, but if you look carefully, if you get close up, you can actually see the volatiles degassing. And it's that brine, that hot brine, that can actually convert the minerals and the crystals almost without them melting or dissolving. It's ionic. It's an ionic transfer. And so we give it a special name. We call it metasomatism. But for all intents and purposes, it is basically hydrothermal activity, hot brines, converting and then concentrating the minerals we're interested in and putting them in things like either layers or in veins, which we can then get at with ease. Sulfides, chlorides and fluorides tend to be the sort of concentrates that we tend to deal with, although obviously our iron-based ones also are very important in most areas. And tourmalinization is what I've already said, when mica and feldspar are replaced with tourmaline. It's not economically interesting unless you happen to be an artist. A friend of mine's an artist and wants to take the tourmaline from Dartmoor and make a painting out of it. I'm not sure that's filed or not, but anyway. But the other rock that might be of interest in the future, of course, is lithium. Lepidolite is a pink mica, which is rich in lithium and comes from these hydrothermal fluids. So it might be in the not too distant future that we've got people reworking some of the tips and spoil for lithium. They're looking at it in terms of Cornwall, and there seems to be no reason, because there is pink mica around Dartmoor. There's no reason why they might not want to look here. Whether we want them to or not is another matter. And then finally, kaolinization, China clay. We eat off it every day. St. Austell is obviously the big China clay pit, and it's got a brother or sister called Leemore on the southwest parts of Dartmoor, which is still being worked. And that simply is when that stuff, the feldspar, weathers quite easily. The sand from the quartz crystals is washed away, and this converts to a white clay called kaolin, and that kaolin then is mined, and they do it in a variety of ways, but we'll come to that later. So to the economic aspects of it, and again I will move quite quickly on that until Andy tells me to stop, but obviously cassiterite, which is tin, and chalcopyrite, which is copper, has been found in hydrothermal veins called elvens, and mined both at the surface and underground. Obviously we get aggregates. The two main types of aggregate we get are the granite itself, which is a beautiful rock for building if it's a good quality granite, so they use it as building stone, or they use it for ballast for rail, as in the Hornfels. And so those are the main activities that in the past were done and then in the present are being done. And China clay is still being mined at Leemore. I'm not sure I believe these numbers. I took these numbers from a textbook. These are the summary of ores produced in Devon, obviously mainly in the 1800s, maybe 1700s as well, but they're very big numbers. 34,000 tons of metal from lead ores of silver, and 26,000 tons of actual metal. Obviously, we know about the tons of tin and copper, but there was also zinc and manganese. Iron, there is lots of iron, but iron is dead cheap, and nowadays is of no value unless it's dug out of a hole in Australia, because they can use big diggers for that. Tungsten, as in wolframite, is quite important and may become more important in the future. Barite or barytes is very important in the oil industry. That might go used as a weight product for the muds that they put down the oil hole in the drilling procedures. But again, I think that might well change with time as the demand goes down. So that's quite a lot of ore produced over time. Now this is Meldon Quarry. Meldon Quarry I've done for a number of reasons. Firstly, you can see that obviously the quarry used for aggregate. This is on the contact zone. And let me just go to this one to summarize it first, and I'll come back. So it's basically to the north, we've got these carboniferous, these not coal carboniferous rocks. And we've got some naps, which I'll talk about in a second. We've got metamorphism from hydrothermal brine, which has given us copper and cassiterite, probably cassiterite, but certainly copper mining in the past. We've got some wonderful apatite dikes, which have unusual rare minerals, which people have been nicking for years, and there's not much left. And some pegmatite lenses of very coarse granite. So all in all, that's quite interesting. Then, of course, we got the quarry itself, which was actually taking out rail ballast aggregate hornfelts, basically, up until 2011. And at its peak, took 300,000 tons out of the ground. On top of all that, of course, the region's got some wonderful tors, the high tors of Yes and High Willets, and, of course, some periglacial features, which we'll look at later. So if you look at the middle map here, middle photograph here, deliberately black and white, because it makes the apatite veins stand out. In fact, these are dikes. They're running vertical to the main outcrop. There's one there and there's one there. And the rest is hornfelts, which, as you can see from the right, in the past they used and dug out quite a big hole, as you can see. So that's the Meldon Quarry. And I've just covered in this region because, as it said, there were two naps, the Greystone nap and the Blackdown nap. What they were just slabs of rock, or groups of rocks of the same age. And when the Variscan orogeny came and bumped into Gondwana bumped into Lorenzia, these two slabs of rock rolled over the underlying rock as great big faults. Firstly, as in A, that green there, by the way, is this green here. And that blue is this blue. And what you can see then is, firstly, the younger Greystone nap went over the younger culm rocks, the carboniferous rocks. And then after that, the blue Blackdown naps went over the Greystone naps, and then the whole thing was buckled. And in diagram, that's the region in the 3D block diagram. There's the mine in here. Okay, and there's the high Willets is there, and this is the granite here, and you can see that's the contact zone. So it's a really nice clear contact zone with all these jagged lines here, big faults. As you can imagine, it's not going to slide over there without causing some sort of disturbance. And in a scheme diagram, this is what happened. Nap coming along, being pushed from the south, overfold, bends over. It can't bend over anymore without breaking, so a great big thrust, fracture, fault, runs across like that, and then it slips over that fault, and you've got, as you can say, an inverted image. And so you also get, apart from these minerals found in veins, outwash. and materials which have been worked and then left. And basically you have trenches at Fox Tor where they filled the waste material into the trenches, and the tin would settle out. It's almost like what it is. It's panning for tin. And the remains of these terraces or little ponds, if you like, yeah, elongated ponds, you can still see at Fox Tor. These alluvial deposits based on density are also found in rivers, particularly on the inside of meanders where it's the lower energy allows it to drop out, and offshore in deltas. And in fact, in South Africa, they go for gold and diamonds, particularly diamonds, in the deltas of the big rivers, the Orange River for one. Then we've got some typical underground works. This is a tin mine, White Works, closed down in 1914 for the last time. You can see details on this on some of the national park material, which, by the way, is in the bibliography. The section on Meldon Quarry and its area is outstanding, by a bloke called Page from Exeter University, I think, and it does an excellent summary of not just the mining, but also the geology and the tectonics. So if you want a quick browse through, it's on the website and well worth looking at. This is Maryvale Quarry. Obviously, it's again on the boundary between the Carboniferous rocks and the granite on the eastern edge, and that's where you've got hornfels and one of these basic igneous rocks that came out during this time as a dike. Again, another hard rock, and they use these hard rocks as quality stone because the dolerite is a very hard stone and the granite is good quality. So very good for building materials. And the same goes for the wonderful little island of tranquility at Haytor, the blue granite, the fine-grained granite, which is an excellent quality building stone. The blue granite, the fine granite, is the one they tend to use, obviously, well, not obviously, because if you've got very large crystals of feldspar and you're trying to dress the stone, you're liable to break it and break it off and it becomes weak. So the finer the grained, the better quality the stone. Now these two, Islesbarrow and Bushdown mines, are basically porphyritic granite. So they've got very large crystals of granite with some fine-grained white apatite in there, with loads which have been worked down to about a depth of about 73 meters. And they reckoned about 300 tons of black tin, i.e. cassiterite, came between 1814 and 1826. And the shafts are still there, and some of the mine buildings, the remains of the mine buildings, are still there as well. But that's not the reason why I put it in. The reason why I put it in was because a group of scientists from Northumberland went down about 5 or 6 years ago and did some gas studies to analyze what safety, they were doing a health and safety check, and they found significant radon gas, 90 times the safety levels inside some of the shafts. Now they concluded that radon 222, yeah, goes to it wasn't that dangerous itself, but of course it breaks down or decays to polonium, which, if you ask any Russian, is a well-known toxic material. And so they have been issuing warnings to people that actually going down the mine shafts and any mines and any explorers, as well as any workers who might in the future want to go down there, got to be really careful that they don't get irradiated to dangerous levels. And actually, you know, they are alpha emitters, both radon and polonium, and so potentially very dangerous if you ingest them. One can therefore extend that possibly, and a lot more work needs to be done, on all the mines that form part of the Cornubian batholith. So one's got to be really careful about that, and just a sort of a little bit of extra. for something we didn't know about in the past. So basically, we got these rock surfaces, these rock types on the top of the mountains or the hills, jointed horizontally and vertically, and lots of discussion about how they formed. They got a strong jointing pattern. It doesn't matter what the rock type is, interestingly, you get them in sandstones, limestones, as well as granites. And basically, the feeling is that they are formed by brine and water in the early days when the rocks are still hot, going down the cracks and opening them up with chemical weathering. And then as those rocks get near the surface, periglacial activity attacks them, and you can see in Haytor the rock jointing there, attacks them and weathers them. And then, as this diagram shows, the weathered material is washed away, forming clitter on the block fields, and therefore you've got part of that landscape. So in a nutshell, the surface is very much reflecting what's happening below. I'll leave you to think about the rock basins that you find, and the lapis also there, as well as the clitter blocks that are lying on the surface. And finally, I've done the summary. Finally, this is the bibliography. So if you want to read further, then obviously these books are very good. And as I say, Shale and Moon is an excellent one, and so are the Dartmoor National Park fact sheets.
Thank you very much, Andrew. That was a fantastic talk, a real sort of blast into 400 million years that we've managed to squeeze into an hour there. So yeah, some really interesting stuff, a lot to digest there, and certainly a lot more than I was sort of familiar with, sort of from the things that I've been doing. So thank you. We've got a few questions along the way, as you'd expect. You excited some prospectors earlier on. Mike Basley was the first to sort of want to know if there's gold on Dartmoor, and even if there is, are you going to tell anyone?
I don't know what. I wouldn't tell you if I did know, but I think there's no reason geologically why not. But because the chemical compositions of these granites and their surrounding rocks do vary between Cornwall and Devon, it seems that because people have looked, there's less chance of it being gold in Devon than there is in Cornwall. Obviously, there is gold in Cornwall. And they have, you mined it for various royal occasions and things. But so if someone said, I've just found a nugget of gold in a river, the River Dart, for example, or wherever, it wouldn't surprise me. I'm not sure I'd spend my time. I'd probably risk it more on the stock market, and that's saying something. So why not go and look for it? I mean, the one thing that there are sort of minerals, and I'm not suggesting people go and pilch these beautiful minerals and things, but for a hobby to actually study the various rare minerals that you sometimes find, particularly if you get permission to go to China clay areas, because those minerals tend to survive the washing out process that China clay processes use, and you can get some beautiful things like amethyst, and that you can get garnets and things in the surrounding rocks as well, the host rocks. So I wouldn't go and rush, but if you, it's just as fruitful as fishing, fly fishing. So give it a go.
Excellent. Thank you for that. Willem asks, why do the granites of the southwest have so much tourmaline in compared to other granites, and why is it black?
It doesn't always black. If you look at thin section, there's a blue hint to it, and the tourmaline is very, very dark blue. But when it's of any thickness, it comes over as black because, of course, it doesn't reflect the light through it very much. The composition of the granites, if you get S-type granites, you get tourmaline is one of the ingredients that you get. One thing about the tourmaline and the process of converting mica and feldspar into tourmaline is the hot brines. And so the different granites have different volatiles, either their concentrations, their temperatures, and things like that. And so it's got to be the right temperatures and pressures, particularly temperatures, and the right chemical ingredients within the brines to allow the tourmaline to replace the micas and the feldspars. So, but tourmaline is not that uncommon in batholithic granites of the Dartmoor type.
Brilliant. That's fantastic. What else have I got here? We sort of rattled through the china clay element, and I think sort of Damien was asking just for a little bit of clarity on the china clay. Where did the china clay fit in with Dartmoor?
Yeah. Okay. Here we go. So here's the china clay. The feldspar that I was showing you earlier on, that yellow, slightly pinky stuff, it varies in color, the feldspar. There are two types: alkali feldspar, plagiaulase feldspar. Potassium and sodium basically are the major things you add on. The metal you add on to the other bit. It's a very susceptible mineral to atmospheric weathering, particularly with things like volatiles, and particularly water. And so that those feldspars will break down to form clay. It's basically hydroxidation, so it's basically adding an OH to it, and of course that makes it very weak indeed. And it's a clay, and lots of granites. I mean, most of the mountains. Let's put it this way: most of the mountains have got cores or insides made of granite. So it's not surprising then that with weathering, the beaches where all this material finally ends up is either sand, which is the quartz grains, or the clay, which is the feldspar. And the speckly bits in the beach are the micas. Now, if that feldspar is a particular type of feldspar, it will form this very clean china clay. And so it basically becomes a white powder, literally a white powder. And so when they find an area where there's been lots of this conversion of feldspar into kaolin through the process of kaolinization, rotting, it's basically rotten feldspar, they can come along, and very often, certainly at St. Austell, where I've seen it worked, they have these great big hoses, power hoses, that fire into the cliff edge and wash out the kaolin into big pits, as you can see on the right hand side here. And the clay settles out, and they dredge out the china clay, and then they send it off for drying out and reworking, whatever it is. And it goes, well, certainly the stuff at St. Austell goes down on the boats and goes out from Foy on big boats to places where they convert it into various things. And it's not just china clay either. They use it for medicines because it absorbs toxins very well. So in the old days, you used to have things like kaolin and morphine, and they use it for chemical processes as well because it's a very good absorbent. So this process, and they're still taking stuff out of their Leamore, but much reduced from when it was at its major activity. But this is linked to, it's the same company that has St. Austell. I think demand, of course, has gone down in terms of china clay, but there's still enough demand to keep them open for the moment anyway.
Excellent. I'm going to give you one more question because I realised that we've gone on till 8:10, so we've been on for a long time. Thank you. Anna Ricketts wants to know a little bit more about the tours, and I feel that's quite a good one to sort of finish with. So she was just talking about the tours that we see today. Would they have been surrounded and covered with softer rock in the past?
The tours have been a big talking point since the 1800s. Obviously, they began by thinking they were sort of human-made, and then they were magic, and gods had done them, and druids, and goodness knows what else. because they look so well structured that it's very difficult to believe that nature's left things piled on top of each other. But there was literally two major theories. One was based on this idea that deep chemical weathering, as the granite came up to near the surface and cooled, jointing due to contraction took place, and then the weathering either from the water from the granite or from water coming down through the groundwater, weathering the material and making the joints more and more, and eventually causing the joints, both horizontal and vertical, to be wide enough that the whole thing becomes weakened. Now, the other one was, it was during the time when this area, during the Ice Age, there is some doubt, or there is some argument whether or not there was a little ice cap on the top of Dartmoor in the northern section. Whether there was or not, it doesn't really matter. What is definitely clear that the majority of Dartmoor was in periglacial conditions, i.e. it wasn't protected by an ice cover from diurnal and annual temperature variations and moisture at certain times and freezing at others. And so the other theory was that frost action got into the joints, and through frost shattering, freeze thaw, and other activities, frost weathering in general, if you like, opened up the joints to make them separate blocks from each other. The reality probably is it's both. So when the granite was underground, we had this deep chemical weathering, which is the picture by the word Pliocene on the left-hand side here, where the waters, both from below and above, went through the joints and opened them up. And then during the Ice Age, when we had very cold and icy conditions, and permafrost, where the ground was permanently frozen, but the surface became moist and started to flow and things, the rock was then exposed due to the surface cover being stripped away due to erosion, exposing these already weathered tops of the granite, and continued to open them up. And then the erosion cleared the debris, if you like, into the hollows, into the river basins, into the troughs at the bottom, and the blocks themselves fell off, gravity, apart from anything else, and left boulders down the slopes. And a thing called solar fluxion is when semi-mobile surfaces slide over the frozen ground below, downslope. And if you've got boulders on the top of that, they'll slide down the slope too. And so we get either what's sometimes called block fields, or in Dartmoor they call clitter, which are this sort of literally a litter of rocks down the slope which have dropped off from the surface. So it's a combination of both, and they're definitely definitely there's the clitter, not human made. One aspect though, sorry, that's the diagram that shows you the clitter going down. So the blue is the mobile zone. The dotted bit, the ground, would be frozen material, and so the clitter slides over down the slope and leaves the next lot of granite to be exposed to weathering. Does that help?
That's great. Thank you for that. That's brilliant. And I think that's a really good one to sort of end on, really, to sort of think that we've taken that journey all the way from sort of the granite sort of intruding into the rocks to form the basis of Dartmoor, and then seeing how it kind of eroded to become the tools that we are familiar with now. So yeah, we've fantastic.
Can I just say one? Sorry, just to add to that one thing, because Haytor shows it quite nicely. You might want to ask the question, why are those joints at a slight angle, dipping slightly down towards the right? And the theory is that as the overburden, these rocks over the granite got worn away, the pressure down on the granite was released, And so it's like if someone's standing on your lungs and they or your chest and they walk away, you breathe out and you expand. It's called pressure release. And as the granite was pressure released, it sort of tipped slightly. Some of the joints tipped slightly away under gravity outwards. And so again, the tores would that would aid tor formation, because as the pressure released, you probably found some of the top bits become unstable and then fall onto the ground and then carried down the slope. Sorry, I forgot to mention that.
That's brilliant. Thank you. Thank you. So that just leaves me to say thank you once again for all of you coming along tonight. Thank you to Andrew for everything that you've done and for giving up your time this evening.